Hi everyone. In this video, we will work through a proof of Clairaut's theorem, which we saw last time gives us conditions under which mixed partial derivatives will be equal to one another. I've decided in this video to focus only on the proof of Clairaut's theorem and to save more about the Hessian matrix for subsequent videos. So we will focus today first on the weaker version of Clairaut's theorem that we saw last time. So as a reminder, this weaker version of Clairaut's theorem says that if we have a scalar field f defined on an open set of R2, and if the partial derivatives d1f, d2f, d12f, and d21f all exist on that open set S, and if d12 of f and d21 of f are continuous at a point A in that set S, then the mixed partial derivatives d12 of f at A and d21 of f at A will be equal to one another. Okay. So here we are assuming existence of each of the first partials, existence of each of the mixed partials, and this existence needs to be on the entire set S. And we are further assuming that the mixed partials d12 of f and d21 of f are both continuous at the point A where we want to establish equality of the mixed partials. But if we have all of those things, then we will get equality of the mixed partials. So we want to take our time to first walk through a proof of this. Okay, so we'll spend quite a bit of the video working through the proof of this. We'll then look at the stronger version and sort of sketch out the major elements of that proof. And I'll sort of point at places where in that stronger version of the theorem, we have to be a little more careful and in fact work through a more detailed analysis. So to begin here, I want to start by just sort of setting up some things for my proof. Okay, so the vector A in our domain, the point that we're at, let's just give that coordinates AB, just in the standard basis. And the first thing we want to do is we want to define a rectangle RHK by choosing values H and K, both positive, such that the rectangle formed by these 4 points, and I'll draw a picture here in a second. The rectangle formed by these 4 points lies entirely within S. So imagine, right, I have my open set in the domain where this function is defined, and I have some point A here. Okay, and imagine this is sort of embedded in the standard plane. So this is the X direction, this is the Y direction. So I have, my point here, A, which again has just coordinates A, B. Okay. Now what I want to do is I want to create a rectangle by moving H in the X direction. So this point would be A plus H, comma, B, and K in the Y direction. So this point here would be, say, and maybe I need to make it a little smaller. K a little bit smaller here. So this would be A, comma, B plus K. And I want to make sure to be careful and choose these values of H and K so that this rectangle, so this is RHK, lies entirely inside of S. So I want to choose these H and K values so that this rectangle still lies inside the open set S where I know all of these partial derivatives exist. Okay, so this final point, this is A plus H, comma, B plus K. Okay, so I want to choose H and K in such a fashion. I know I can do that because A is an interior point of S. Why is it an interior point of S? Well, S is open, so every point is an interior point. Okay, so we'll sort of take this, and I'm actually just going to go back and think about this rectangle. So you can sort of imagine we're going to take and just zoom in here on this rectangle. So this rectangle then is just a rectangle consisting of the 4 points. A plus B, or sorry, AB, A plus H, B. This is A plus H, B plus K. And this is A, B plus K. All right. So we're working on this. We're really going to work on this rectangle. This is what we're calling R of HK. Okay. And now we're going to define this function delta HK. Okay. And it is a function of H and K, but you can really just sort of think about it as this sort of quantity we're going to be looking at. So I'm going to define delta HK as this first line. Okay, so that's my definition of delta HK. Now, it looks sort of complicated, but if you notice in brackets here, in this first term, the A plus H is not changing. So I'm looking at a difference between f of A plus H, B plus K, and f of A plus H, B. So I'm really looking at the function f evaluated at this point and at this point, and I'm taking a difference. So I'm looking at the difference, how f changes from this point to this point. This difference is how f changes from this point to this point. And then I'm taking a difference of those two differences. So I'm looking at how much does f change from here to here versus how much it changes from here to here. Okay. Now, if you sort of think about that for a minute, that actually is starting to sound something like a second derivative. Each of these differences is, in a way, capturing information about how the function f changes, in this case, as y changes, right? My y value is changing from b plus k to b. This is, again, capturing how f changes as y changes, okay? And then I'm measuring how those changes with respect to the y variable change as I change my x variable. So somehow it does seem like this should encapsulate some sort of information about a mixed partial derivative. All right, so I'm defining h in this way, but notice if I do this, it's actually exactly equal to this. Now, if you look at this is a difference here, but this is the difference between f at these 2 points. So this is measuring how f changes with respect to changes in x. And then the second difference here is measuring changes with respect to x. So each of these is sort of encapsulating a change with respect to x, but then I'm measuring the differences between those two as my y values change. Okay. So again, each of these two expressions are equal to one another. So you'll notice all I've done is swap these interior terms, right? And they were both negative here and they're both negative here. So again, I'm not changing the value of this. H is defined in this way, and this is equal to this, okay? But notice that by formulating it in these two ways, I'm already seeing that these are sort of measuring different types of mixed partial derivatives. So hopefully these are like discrete derivatives. Hopefully I can somehow apply limits appropriately, do some appropriate analysis to show that this leads me to the equality of mixed partials that I would like. All right, great. So as you might guess, we're sort of going to work on each of these formulations of of delta HK in turn. Okay, so we'll start with the first one. We'll see what we can say about it, and then we'll use the second one and see what we can say about it. All right. So let's start. This is, again, just that first definition of delta HK. Okay, so I've just put it here at the top because we're going to be working on it quite a bit. Okay, so what I'm going to do is I'm going to start and I'm going to define a function g of x. Okay, and sort of what I want to notice is that each of these, right, this quantity in brackets here, these each have an f of a plus h, and then the y values are different here. But the y values are b plus k and b. Same thing here, the y values are b plus k and b, and the x values are the same. So I'm going to define g of x to be f of x comma b plus k minus f of x comma b. So again, notice that this is taking the form of each of these things in brackets. It's just that here this has the x value a plus h, and here this has the x value of a. Okay, so what I'm really saying is that if we do that, then delta hk, I can just express that as g of a plus h minus g of a. Right, so this quantity in the first set of brackets just becomes g of a plus h. This becomes g of a. All right. Well, now I can apply, let me actually, I'm not right equal here. I'm going to now apply, I want to eventually get this to something about a derivative. So I'm actually going to apply the mean value theorem to this quantity g of a plus h minus g of a. So by the mean value theorem, there exists some point, I'll call it x1, between a and a plus h, such that g prime of x1 times h is equal to g of a plus h minus g of a. Now, if this maybe isn't immediately clicking, if you divide both sides by h, this is maybe the form you're used to seeing it in. G prime of x1 is equal to g of a plus h minus g of a over the difference between these, which is just h. Okay, but I've just reformulated this here because I want to rewrite it using this. Okay. So we now really have delta hk is equal to this. But further, let's note that what is g prime of x1? Well, g is this g prime of x, that's taking a derivative of this with respect to x. If I were to take a derivative of this with respect to x, that's really taking the partial derivative of f with respect to the first variable. Okay, so g prime of x1 is partial derivative with respect to the first variable of f evaluated at x1, b plus k, minus the partial derivative with respect to the first variable of f evaluated at x1, b. Okay. And doing all this, we have all of this happening so that now I can write delta hk as what? So let's see, delta hk was equal to this, but this was equal to this. So I really have h times g prime. So I have that this is h times g prime, which is now equal to this. All right. Now, I sort of look at this, I've got a difference of two things. The x1 is the same. What's changing here is the y variable. Okay, so now let me define another function, g of y, and I'm going to define this to be d1 f of x1 comma y. Okay. If I do that, now this is my delta hk. This is h times, this would just be g of b plus k minus g of b. And now again, I want to apply the mean value theorem. So this is going to be equal to h times, now here, this difference will be equal to the difference between these two, which is k, times g prime of some y value, call it y1. But g prime of y1, that's going to be actually the derivative with respect to the second variable of this thing. Oh, I left out my h and my k. Oops. Evaluated at x1, y1, and this is for some y1 between b and b plus k. All right, so the sort of moral of the story here is that we have here delta hk is equal to h times k times, this is really just d21 f of x1, y1 for some pair x1, y1. Well, let's see. X1 was between a and a plus h. Y1 was between b and b plus k. So x1, y1 is in this rectangle RHK. All right, awesome. Now, we essentially want to try and repeat this same analysis, but we want to switch to the alternate formulation of of delta HK. All right, so notice again, this is what we just did. You watch the top line, it's going to swap the inner two terms, right? Now we want to redo this analysis, but for this formulation of delta HK. Now, I want to work through this fairly quickly, and I'm going to keep a lot of the same language here because you're going to see that really the proof is the same, just some of the accounting changes slightly. Okay. All right. So to begin here, right, if I look at each of these, what's now fixed is the a plus HA, a plus HA. Okay, so we're actually going to define a slightly different function. Okay. What I'm going to do here to help us see what structure changes and what doesn't is I'll switch colors. So I'm going to define a new function, let's call it h of, actually h of, now this is going to be y. Okay. And it's going to be defined as f of a plus h comma y minus f of a y. Okay. Doing that gives us that delta hk then is, oh, in this form, now this first part is h of b plus k. And the second part is h of b. Okay. But again, by the mean value theorem, there exists, okay, now I don't want an x1, and it's going to be a y value, and I already have one y value, so I'm going to call this y2. So there's going to exist a y2 in b to b plus k such that I know I'm being a little pedantic about just keeping like these parentheses, but I want you to see like we're changing a lot of the names of variables, but the ideas are really the same. So by mean value theorem, there exists a y2 such that h prime of y2 times k, because k is now the difference between these, is equal to h of b plus k minus h of b. All right. Further, we note that, okay, h prime, we'll look at h prime of y2. What's that going to be? H prime of y2. So if I want to take the derivative of this with respect to y, I need to take a derivative with respect to the second variable. So this is going to be a derivative with respect to the second variable of f of a plus h comma y2 minus derivative with respect to the second variable of f of a y2. And then so that now we have delta hk is equal to, we have now not a factor of h, but a factor of k, d2 of a plus h y2 minus d2 of f of a y2. All right, now we're going to define another function. Okay, let's call this little h of x. And remember, the idea here was that the function little h of x should sort of capture that these are the same with respect to the y value. So I'm going to define this to be d2 of f of x y2. Then I can re-express delta hk as that k factor is still hanging out front. Well, actually, let's leave this alone for a second. We'll come back and fix this in a second. So this is a k factor hanging out front. And now this is going to be an h of a plus h minus h of a. Now, I apply mean value theorem here. Okay, so there exists some point. This is going to be an x value, and we'll call it x2. This is going to be for some x2 between a plus h, or sorry, between a and a plus h. Okay. And so applying the mean value theorem, we'll get an h from the difference here. That'll come out with the k. So now we're going to get an hk, which is what we had before. And here we'll have the function, and it'll be an h prime of x2. Okay. But what is h prime, little h prime of x2? That's a derivative with respect to the first variable evaluated at x2. So this is now a d1, d2, f of x2, y2. But now if we come down here, what we get here, right, is, and I'm going to leave this, this is the old one, we've now proven that delta hk is equal to hk d12 f of x2, y2 for some x2, y2. And again, because of the conditions on x2 and y2, they're also in this rectangle RHK. All right. So all of this work that we've done. So first, notice that yes, we've changed the names of a lot of the variables and slightly redefined some of the functions, but fundamentally the proof is the same. You're just using the two different formulations of delta HK. Okay. Now, let's take away some of this and see how we can use these last two lines then to finish off the proof. Now, while I'm erasing, I'll say the tempting thing is to look at this and go, okay, I can set these two things equal to each other, and I have what I want. I have that the mixed partials are equal to each other. Well, we have to be a little bit careful because we have that mixed partials. There are some mixed partials that are equal to each other, but these are at different points, potentially, right? So we've somehow got to rectify the fact that right now we have equality of mixed partials, but those mixed partials are being evaluated at different points. And we really want them both to be equal at AB. All right. So if we just sort of take these two lines, well, This is equal to delta HK, and this is equal to delta HK. So we really should have that these two things, right, are equal to each other, right? So, okay, that's great. And H and K, they're both positive. I can just come up here and divide both of these, right, by HK. And I mean, technically, I should also divide this middle piece by HK, right? But I'm really just looking at these two things. So I really have D21 f of x1, y1 is equal to D12 f of x2, y2. Okay. Now to finish the proof, okay, again, I really want these at the same point. Now all I need to do is take a limit. Okay, so if I take a limit as h and k go to 0, okay. Well, okay, as h and k go to 0, what's going to happen to x1, y1? Well, remember, so as h and k go to 0, we have this point AB. This rectangle is collapsing down to a point. Now, I know that my point x1, y1 is somewhere in this rectangle. I don't know where, but it's somewhere in this rectangle. But as h and k go to 0, by the squeeze theorem, right, both x1 and y1 are going to be forced to this point AB. Okay. And similarly, x2, y2 is going to be forced to AB. So now if I look at this side, I can take a limit of both sides as h and k go to 0, and invoking the continuity of each of these mixed partials at A, we have that D21 f of AB, that's going to be equal to the limit as h and k go to 0, 0 of D21 f of x1, y1. So this is using the continuity of D21. This is using this equality we've already established, right? I'm just taking the limit of the same thing. These are the same thing. And by the continuity of D12, this is just equal to D12 f of A, B. And so what I have established here is that the mixed partials up here, I have that the mixed partials were equal, but at two different points. But by taking a limit and forcing this rectangle down to the single point AB, using the continuity of the mixed partials, I'm able to recover that D21 of f at AB must be equal to D12 of f at AB, which is exactly what I set out to prove. So that completes the proof of this weaker form of Clairaut's theorem. Now, we'll sketch out the proof of the slightly stronger version, but I'll just point out, right, I've pretty heavily used here continuity, right? Certainly, at least the continuity of D12, right? I use the continuity of both of them. But if I'm going to get rid of continuity here, I'm going to have a problem. I also used the existence of D12 earlier on when I took the derivative of, let's see, in that case, it must have been when I took the derivative of, let me check my notes here. When I took the derivative of little h, I believe I used the existence of that mixed partial. So somehow, if I want to try and get rid of the requirements on one of the mixed partials, I'm going to have to do something a little bit different. This isn't totally going to be reproducible in that case, although we'll see that like a good part of it will be. So just to remind ourselves, the stronger form of Clairaut's theorem, right? Really what it does is before we assume the existence of the first partials, d1f and d2f, and we assume the existence of both mixed partials. Now we're only going to assume the existence of one of the mixed partials. We chose d21, you could choose d12. And I put this up here. This, as I wrote it last time, is actually incorrect. You need more than just continuity at the point A here. You need that this is continuous on S. So I did want to fix that in this video. So you actually need more than just continuity at the point A here. You need that partial is continuous on S. If you assume that, then the other mixed partial must also exist, and the mixed partials must be equal to one another. Okay. So what I want to do is conclude this video by spending a little bit of time just sketching out some of the proof and where some of the differences would lie if we wanted to prove this stronger version. All right. So it turns out that there's sort of a good first part of the proof that can be reused. Okay, so the first thing you do is you just show you're going to use that same delta H sub k. Okay, you're going to use that same expression, and just as we did before, you'll be able to show that delta HK is equal to H times K times D21 F of X1, Y1. Okay, so that was sort of that first formulation of delta HK we went through. We proved this. You can still do all of that the same because all of you're using there is the existence of first partials and the existence of the mixed partial D21 of F. Okay. Now, if you try to use the second formulation and go through the proof again, you run into a problem, which is you don't know that D12 of F exists. Okay, so somehow then we have to do something a little more nuanced there. Okay, so to just again give you some idea, what we have to do is we have to go back and say, okay, what is we need to establish the existence of D12 of F at AB. Okay, and just to give you some sense, you sort of just write out, okay, what is this? So D12 of F at AB. By definition, this is the limit as H goes to 0 of of D2 F of A plus H comma B minus D2 F of AB all over H. Okay, so that's just the definition of the mixed partial derivative. Okay, and so you really work on this sort of limit here, and so you go, okay, well I need to know something about D2 F of AB and D2 F of A plus HB. So you sort of write down what each of those is. So D2 F of A plus HB. Well, what's that defined to be? That's defined to be the limit. And I want to use something different here. I'm going to use K here. That's generally going to be my increment in the Y variable of F of A plus H comma b plus k minus f of a plus h b all over k. And similarly, I can write down d2 f of ab is the same thing. It's just the limit as k goes to 0 of f of a comma b plus k minus f of ab all over k. Okay. So again, we want to understand this. To understand this, we need to understand each of these. So we write out what each of these are. And then, excuse me, we notice if I look at this difference quotient here, okay, and I can sort of write out, basically sort of substitute this in here, okay. Sorry, just looking at this, right, this difference quotient here, right? This would be the limit. Let me put some brackets here. Just trying to understand the difference quotient here in the orange brackets, okay? You would do this limit minus this limit divided by h, okay? And you can break the limits apart, and what you actually get is that this is equal to the limit as k goes to 0 of delta hk all over h times k. Okay, sorry, you get that this difference quotient, all that stuff implies that the difference quotient, d2 f of a plus hb minus d2 f of ab all over h. So this thing in orange brackets is actually equal to this, the line here. And now you need to take a limit as h goes to 0 this. So d1, 2 f of ab should be the limit as h goes to 0 of this thing in orange brackets, but that thing in orange brackets is the limit as k goes to 0 of delta hk over hk. Yeah. Now, when you start to look at this, okay, you're tempted to, so if you sort of look up here, okay, delta hk divided by hk, you have that this is equal to the limit as h goes to 0 of the limit as k goes to 0 of d21 f of x1, y1. Okay. And you feel like you're so close. Like you feel like you want to say, oh yeah, I have continuity of this thing. And so as k goes to 0 and the h goes to 0, these will both go to AB and I get what I want. Okay. The problem here is that we don't necessarily know that as k goes to 0, so as k goes to 0, right, this point y is going to move, but x is also going to move. So x is not fixed, nor is x necessarily even approaching any limit. So the problem we have is that as k goes to 0, this y1 is going to be forced to b, but x1 is also changing as we change this k value, okay, because our rectangle is changing. Okay? And so we have a problem in that we don't know what happens to x1 as k goes to 0. So this is where we have to do just a more subtle analysis. So the sort of last step here is to show that this limit, this iterated limit, as h goes to 0, limit as k goes to 0 of d21 f of x1, y1, you need to show that this is actually equal to d21 f of AB. Now, to do this, you have to do just essentially a delta epsilon sort of analysis, slogging through that. The computation is done on page 280 and 281 of Apostles' book, if you want to go see that. I don't really want to spend the time to do that, mostly because I don't think we learn a lot more about why this is true. I really like the weaker version of this theorem because it really emphasizes why the mixed partials are equal. Here, you're really trying to relax some conditions to show that just the existence of one of the mixed and continuity of one of the mixed partials could be enough to give you the existence of the other mixed partial. So I don't want to spend a whole bunch of time sliding through that, but if you want to see it, it is on pages 280 and 281. I think the full proof runs like page 279 to 281, but you can see that full proof in the book if you want to sort of fill in that last step. But this at least gives you some idea that some of the analysis is the same for the stronger version. You need to do a little bit more, and then you need to show, lastly, this iterated limit, which ends up being one of the more technical parts of the proof. So we will end this video here. As I said at the start, I'm going to push the material about the Hessian matrix off to the next video. But what I would encourage you to do before that video is to think back. We've been talking about mixed partials as sort of a type of second derivative, but right, they're also like the mixed partials d11 and d22, right, which are not mixed partials. We somehow would like these second derivative type things to tell us the same types of things that, say, second derivatives told us for functions from R to R. So, for example, a function from R to R, I often thought about concave up versus concave down, right, by just thinking about the second derivative. How did that go? Why did that work? So if you haven't thought about that in a while, go back to the stuff from 5610. How do you prove a second derivative test, for example, right? If I'm at a critical point and the second derivative is strictly positive, then I'm at a local minimum. If the second derivative is strictly negative, I'm at a local maximum. If the second derivative is 0, it's inconclusive, right? And just start to think about, like, could we do something like that for functions of multiple variables? The answer, it turns out, will be yes. But just as we had to do things a little bit differently for first derivatives, we're going to need to do things a little differently for second derivatives. And in particular, we're going to need to think about a second order Taylor expansion for a multivariable function to help us identify what the right notion of second derivative is. And that notion will be that of the Hessian matrix, which encapsulates all of the information about all of the second partial derivatives that will then help us determine things like whether we're at a local maximum or a local minimum if we're at a critical point. So we will cover that beginning in the next video.